This is a very good problem to understand rigid body dynamics. This problem appeared in 2014 International Physics Olympiad held in the city of Astana, Kazakhstan. Let us understand the problem given here. There is a hollow cylinder kept on a rough horizontal surface. Inside the cylinder, there is a puck held against its surface at a height r. The system of cylinder and the puck is released from rest as shown in the figure, and we are asked to find the interaction force between them when the puck is at its lowest position. So to begin with, let us draw the final situation we are interested in. Let's say this is the cylinder. That's the horizontal ground. Now, when the puck is at the lowest point of its trajectory, we are asked to find the force of interaction between them. Now, in order to do that, we need to know the velocity of the puck relative to the center of mass of the cylinder. So, at this instant, if I take the center of mass of the cylinder, and then from the problem we can guess that as the puck moves to the right, the cylinder must move to the left. So let's say the center of mass velocity at this instant of the cylinder is v1, okay? And the velocity of the puck to the right is v. So here, since we are taking subscripts 1 and 2, 1 is used to represent the cylinder and then 2 is used to represent the puck. Now here, if we can get the relative velocity, okay, so the relative velocity between them, basically the velocity of the puck relative to the center of mass of the cylinder, because they are moving in the opposite directions, is v1 plus v. So if we can get this value, I think we can figure out the interaction force between them. Now, so how do we proceed forward to get this? Okay. So one hint that the problem gives us is, even though between the cylinder and the horizontal ground there is friction, the cylinder moves without slipping. So basically the cylinder rolls without slipping. So that means there is no mechanical energy loss. So we can use the conservation of mechanical energy and then begin by writing at least the first equation. So here the gravitational potential energy law must be equal to the kinetic energy gain. So what is the gravitational potential energy lost? It's only due to the puck. It descends by height r. So the gravitational potential energy lost is mgr. And the kinetic energy gained is the kinetic energy of the cylinder, which is half m v1 square. Now here we have to be careful. Because the cylinder is rolling without slipping, the cylinder will have a angular velocity in the counterclockwise sense. Now, why in the counterclockwise sense? If you look at the point of contact, so for a moment, forget about the puck. If you look at the point of contact of the cylinder that is touching the ground, it will have center of mass velocity v1 to the left, and then the tangential velocity is to the right. So if these two vectors point in opposite directions and if they are equal in magnitude, if v1 is equal to r omega, the tangential velocity, then the point of contact will not slip relative to the ground. So here we could use this omega in our expression. So to begin with, we can just write the rotational kinetic energy, which is half I omega square, and the kinetic energy of the puck is half m v. So here we can say half m v1 square, and if I look at the relation here, omega can be written as v1 by r, and the moment of inertia of the cylinder, hollow cylinder, is mr square. So here we have v1 by r square. So that is good news. So we have eliminated omega, half m v2. So this, I think we can write it as mgr is equal to, I think the first two terms we can combine is m v1 square plus half m v2. Now we have one equation with two unknowns, so we need to figure out how to get a relation between them. Now again, keep in mind that there is friction between the cylinder and the horizontal ground. So even if we take our system here, I'm sure you guess this, that we cannot use the conservation of linear motion. So we'll have to look at a different approach to get the relation between V1 and V2. Now let us look at the free body diagrams of the puck and the cylinder at an intermediate position. If you look at the puck, the cylinder applies a normal force towards the center of the cylinder. Let's call it N. And the earth applies gravitational force as usual in the downward direction. So that's mg. Okay. So if I say that the puck has an acceleration to the right, which is taken as a2. So if you look at our convention, I think 2 refers to the puck. And here we need to resolve the normal force along the horizontal. So if I take a component along the horizontal line, we get n sine theta. So we can write here for the puck at an intermediate position, n sine theta is mass of the puck into acceleration. Now let us look at the cylinder. Now Newton's third law dictates that the puck would apply a normal force on the cylinder away from the center of the cylinder. So again n, and there is gravitational force in the downward direction. The gravitational force capital Mg is in the downward direction, and the ground is also applying a normal force in the upward direction. So let's call that as M. Now here, if you take a component of the normal force applied by the puck on the cylinder, it would be n sine theta. But we have to be very careful here because that's not the only force in the horizontal direction. Now because the cylinder is gaining the center of mass acceleration to the left, so let's say if we call that as A. In order to roll without slipping, it should have angular acceleration in the counterclockwise. Now that is provided only because of the friction between the ground and the cylinder. So let's say the friction must point to the right. Okay. So here, if I use the Newton's second law for translation, we can write n sine theta as n sine theta minus friction should be mass into acceleration. And about the center of mass, only friction is trying to provide the angular acceleration, and all the other forces are passing through the center. So the counterclockwise angular acceleration is provided by the torque due to friction. So we can write F into R is I alpha. And again here, F into R, the moment of inertia, we have seen it is mr square, mr square for hollow cylinder, and alpha, because it is rolling without slipping, again a1 should be equal to the tangential acceleration of the point of contact, so which is r alpha. So here alpha can be written as a1 by r. So if you look at this, the friction is m into a1. So from here, I think we can write n sine theta as capital M into A2. So here clearly, oh sorry, so this is A1. So clearly, I think I made a mistake here. If I substitute M A1, I think it should be 2 M A1. Yeah. Okay. So from here, we can say that 2 capital M A1 is M A2. Now we can write acceleration as a derivative of the velocity with respect to time, and then we can see that we can actually get a relation between the velocities. So if I write down 2 capital M into dv1 by dt, this is equal to, oh sorry, the other one. So M into dv2 by dt. So here I think we can forget about the time variable. So 2 capital M, if I integrate on both sides, so dv1 is equal to M and then integrate dv. So at the beginning, the initial velocity is 0 for both of them. So when the puck reaches the bottommost point, we can say the velocity of the center mass of the cylinder is v1, that's what we said, and the velocity of the puck to the right relative to the ground is v. So here if you integrate this is really a trivial integral, so we can just write 2m into v1 is equal to m into v. So now we have a relation between v1 and v2. So now we can go back to our equation here. Mgr is equal to mv1 square plus half mv2 square. So we can use this to get the values of v1 and v2. So let's do that. So if I substitute v2 here, I have mgr is equal to capital M v1 square plus half m. What do we have? v2 I can write it as 2 capital M v1 by 2 capital M v1 by small m also. Here capital M v1 square is a common factor, so and then we have 1 plus, so there will be capital M. I think in the numerator it is 4, so we can write it as 2 capital M by small m. Okay, so here we can write v1. So v1 would be, so I can just write it as m to square root of, so this m goes to the left hand side, that's m square, so I'm pulling that m outside, and then we have d capital R by capital M into small m plus 2 capital. So that is v1. Now so take this v1 and then substitute here. Okay, so we get v2 as 2 capital M by small, and then v1 is capital M, sorry, small m into square root of, yeah, so gr by capital M into into 1 plus small m plus small m plus 2 capital M. So here this can be written as 2 capital M into square root of g the capital M to small m plus 2. Now, if I, let's say, write v1 plus v2, so that's the relative velocity, write it here. So v1 plus v2 is the relative velocity. So v1 was this. So I think if I look at, maybe just write the common factor out. So I have the common factor between v1 and v2 is square root of gr by capital M into small m plus 2. And then from let's say v1 we have and then from v2 we have 2 capital. I think we can see this. So from here we can write the relative velocity is square root of gr by capital M multiplied by small m plus 2 capital. Okay. So now finally, if you look at the free body diagram of the path, when it is at the bottommost point, the interaction force acts towards the center of the cylinder, and the gravitational force acts at mg. So the net force towards the center provides the necessary centripetal. So if I use that finally, so let's say the net force towards the center is F minus g, and that is equal to the mass multiplied by centripetal angle, is v square relative by. Now if I substitute the square of relative velocity, I think we can just take whatever is inside the root, so that is gr by capital M into small m plus 2 capital. So here F minus M, so this would be mg. I think maybe capital M I can take it inside. We have small g, then 2 plus small m by capital. So if F we write alone on the left hand side, I think mg you can take it to the right hand side. I think this is easy to do anyway. So it's like I have 3 plus small m by capital